of interstellar gas. Our Sun, for example, passes through the local interstellar cloud at a speed of about 25 km per second. But Mira really stands out in this respect, as it whizzes through gas in interstellar space at a speed of 130 km per second. As a result of such staggering propulsion, the shed material is blown back, thus forming the unique tail we can marvel at. This tail is the feature that makes Mira one of the most peculiar stars in the Cetus constellation. The tail of this star was discovered in 2007 with the help of the GALEX Orbiting Ultraviolet Space Telescope. A group of astronomers received high-quality ultraviolet light images of Mira where the tail, made up of gas and dust, can be clearly seen. At first, this tail formation rather perplexed the scientists, as the star had been under observation for over 400 years, and no tail had been spotted before. But the riddle was soon solved. Only ultraviolet images were able to reveal the tail, and only regular photos had been taken before. The length of the tail reaches 13 light-years, which is 3 times the distance from the Sun to the closest star, Proxima Centauri. As I've already mentioned, it was formed by material being shed in the course of the star's movement through space. Every 10 years, Mira sheds approximately as much material as the mass of our Earth. By estimating the length of the tail and the star's velocity, the material found at the very tip of the tail was gauged to have been dumped as long ago as about 30,000 years. As for the total mass of the material shed so far, it may be as much as 3,000 Earth masses. Marvelous as it is, the tail isn't the only feature that singles out Mira among other stars. Another feature it has is a bizarre formation that can also be seen in images beamed back from the GALEX telescope. It most likely originated as a result of Mira's speed with which it travels through the molecular cloud. A kind of bow we can see in front would have been accumulated in the many years as a result of the star's material at the front colliding with particles of interstellar gas. That makes Mira resemble a boat cutting through water, only Mira cuts through space instead. Most of the shed material is made up of atoms of hydrogen. Once shed, they gradually lose their impetus and release the energy in the form of ultraviolet rays, and it is these rays that were captured by the GALEX telescope. We know Mira as a binary pulsating variable star. In its maximal luminosity periods, it flares up to be the brightest star in its constellation, but even with its luminosity at its lowest, it can still be seen through regular binoculars. The best time for observing it from our Earth is October and November. Billions of years ago, this object used to be a yellow dwarf, and today, Mira's stellar travels are coming to an end, as it is now in one of the final stages of a star's life. Speaking about its system, it comprises 2 stellar companions, Mira A, a red giant, and Mira B, a white dwarf. Both objects are about 417 light-years away from our Earth, and the distance between the companions themselves is 70 astronomical units. The first component in the system is a pulsating variable star, with the average apparent magnitude 3.5. Depending on the phase, however, the value may fluctuate between 10 and 2. Just to compare, the apparent magnitude of Sirius is minus 1.46. The mass of the system's first component is approximately 1.2 that of the Sun. Interestingly, its radius is 360 times that of the Sun. The reason for such impressive dimensions and a comparatively small mass lies in the fact that since Mira A is a red giant, its average density may be thousands of times less than that of water. Just to compare, the average density of the Sun is slightly bigger than that of water. Besides, a star hitting the red giant phase gets a massive growth spurt, and with a mass comparable to that of the Sun may in theory grow to the size of the Earth's orbit. The surface temperature on Mira A reaches 3000 degrees Kelvin. The luminosity of the star, meanwhile, is 9000 times that of the Sun. As for its supposed age, it is estimated to be 6 billion years. The red giant is not massive enough to go supernova at the end of its life cycle. Instead, it is going to expel its outer envelope and gradually turn into a white dwarf. The expanding outer envelope forms a planetary nebula, which will later on be dispersed in space around it. As for the second component, Mira B, it is a white dwarf already. As this object is located close to Mira A by space standards, it attracts material dumped from the outer layers of the red giant. In this manner, a hot accretion disk was formed around Mira B, and since matter is shed onto it at irregular intervals, Mira B is a variable star too. Its apparent magnitude fluctuates between 9.5 and 12. Thus, both components in the system are variable stars, or variables. Other stars in the universe, whose luminosity depends on physical processes taking place in their vicinity, also fall into the same category. It is important to study these objects in order to understand the nature of stellar evolution, as variable stars are more often than not at a turning point in their existence. In fact, the phenomenon of Mira is a perfect demonstration of how objects reaching some milestone or other in their life may conceal a number of great riddles. Mira's unusual features allowed scientists to use it as the prototype for a special classification for such-like objects that got the name Mira-type stars or Mira variables. Celestial objects of this variety are pulsating variable stars of late-type spectral classes, with the values for their apparent magnitudes ranging from 2.5 to 11. Mira variables are giants that shed their outer envelope in the course of several million years and eventually turn into white dwarfs. Mostly, Mira-type variables shouldn't be heavier than 2 masses of the Sun, although they may be thousands of times brighter than the Sun on account of their expanded outer layer. The pulsation of these objects occurs due to regular contraction and expansion of these stars. This also causes changes in the radius and temperature, resulting in variable luminosity. As for the chance of planets possibly hiding somewhere in these stars' orbits, only one Mira-type variable boasts an unconfirmed planetary system, R Leonis, in the Leo constellation. It goes without saying that the information about Mira possessed by science today is rather sparse. We really have no clue if there are planets or some equally amazing space objects located close to it. But it is safe enough to say that this star is yet to hit the headlines, and for all we know, it may happen literally at any moment. If you'd like to be the first to be updated on this one, stay with the Cosmo channel and feel free to subscribe to our channel in Telegram, where we post the latest scientific news. Dear friends, I hope you enjoy the stuff we share about all those celestial bodies in space. If you'd like to support our project in addition to a like or a comment, feel free to follow the link to Patreon. It's in this video's description. Your encouragement motivates us to carry on making new videos about awesome objects in space. And as you watch, our channel keeps growing. Let's keep in touch.